My talk today is related to some work I'm doing on behalf of the National Building Code. We have a new code coming out, hopefully in 2015. The ground motions will be changed quite a bit in that code, and probably also the amplification factors. Now, I'm dealing with one very small part of that right here today, and that is thin layers, thin soft layers on top of hard substratum. How do they affect the amplification in code terms? Now, the present code is 2010, that's 2010. Before that, as you know, the North American codes are all based on the average shear wave velocity over the top 30 meters. Now, when you have a shallow layer on the surface, the only way you can make up the 30 meters is include some of the hard layer in there as well. Before 2010, we used to do that with one restriction. Because of the higher velocities of the hard layer, there was always a chance that we might be bumped into one of the really high, stiff layers like A or B. Our reference site is C. So we put that restriction that no matter what the velocities were, we couldn't get a rating higher than site class C. For the present code, we changed that. I can't remember why. And we changed it to determine the amplification of the surface layer by using the properties of the layer itself. In other words, the average shear wave velocity in the surface layer. But the surface layer is not 30 meters. So there's really not much of a foundation for that. So we decided to look into that. My co-author, Francisco Rubuz from Chile, was interested in doing that because he was interested in the Chilean ground motions. However, we found that we didn't have enough recordings on hard soil to actually do anything with it, so we switched to Japan. This summarizes what I said a moment ago. So what I'm trying to do now is to check whether our new rule that you use the average shear wave velocity in the surface layer works or not. Now, the simple model that you can think about, you have a hard layer, you have a softer layer overlying it. Let's assume for the moment that it's uniform, homogeneous, and elastic. Then the period of that layer is 4h over Vs. That's the fundamental period. And in any dynamical system, the fundamental period plays a big role in the kind of response that you get. If not that period, then one of the higher periods. But it's always one of the modal frequencies that is going to boost your amplification. Amplification has two meanings. When we're doing design, we go to the database and we pick up a ground motion on hard soil, and we feed that motion into the system. The peak ground acceleration here is A0. We feed it in, it comes up, and we get AT on top. And then we say the amplification is AT over A0. Now, these are both surface motions, so they both have a factor of 2 for amplification at the surface, which cancels out when we take the ratio. But the data that I'm using today is borehole data. So the motion is not, in the rock is not exposed, it's inside. So we're coming up this way. And we're getting the amplification, we're getting the ground motion here, and then we're looking at what's up here, and our amplification will be from here to here. Now, this is the partial set of Japanese data. You can see that, number one, sorry, I can see why Perry had a problem this morning. That's pretty shallow. There is one thick layer that we left it in there. And then there's one that's exactly 30. But all the rest are less than 30, and the deepest one is 18. The shear wave velocities are over here. We have about another 30 or 40 ground motions that we're analyzing at the moment. Down in Chile, he's doing it. Francisco's doing it. We're not finished yet. Now, these motions have been studied already, and even in Canada by a colleague of ours on the code committee. And but they did not deal with the motion up at the top of the rock. They considered amplification from the bottom of the hole to the ground surface. And some of those depths are huge. I'm sorry. See, they go as low as 200, 500, 300. So the amplification is with respect to that, with the assumption being that not much amplification occurs in the rock. I'm anticipating some of our results by showing you that that's not right. These are the motions at the top of the rock. This is the ground surface, top of the rock column, and this is the bottom of the rock column. And you can see that the amplification is substantial, probably an average value of 2. Now, how am I going to get the motions on the top of the rock? Well, the answer is easy. You analyze it. But you must validate. For your motions at the top of the rock to be useful and valid for using, you must demonstrate that your analysis is working for the data that's already recorded. So that was our next thing. Now here is the rock motion, the spectrum of the rock motion. Measured at the surface is this color. It looks purple here. It looked red in my slide, but that's all right. And this is the calculated one. Now, we missed details, but I would say that is about as good as you can get if you're honest about it. And we certainly didn't try to make it look better. I'm going to show you some others that are not so good. I want to give you a fair representation of what we actually did. Now, then, our colleagues who worked on it earlier were measuring the amplification from here to here. We're doing it from here to here. So this is the amplification within the soft layer. And this is the amplification in this case within the rock. In this case, it's bigger than up here. That, of course, is not always the case. Now let me show you a few more. This one isn't quite so great, but it's good enough. We're talking about engineering. We're not talking about nanoseconds or trying to get a rocket to the moon without deviating too much from a through path. Engineering terms, that's not bad. Now, we calculate for this. We calculate the motion at the top of the rock. Here it is. This is the missing element. I'm surprised they didn't put an instrument at the top of the rock, but they didn't. And you can see that now there's a more substantial amplification in the soil itself. And then down here, well, the factor probably isn't all that different, but the numbers are certainly different. And I think I have one more, yes. This one is pretty good, too. There's a bump there. Oh, sorry. There's a bump here that we didn't get. But as far as the amplification is concerned, it's pretty good. And over here, this is the calculated motion in the rock. So our amplification is between here and here. Now, how good is VS30? Can we calibrate the amplification against VS30 and see how it comes out? Well, here you go. Here is the data that I just showed you. Here is a fit to the data. It's a nonlinear fit to the data, nonlinear regression. And here is plus and minus 1 standard deviation. And the correlation is 8.8. That's quite good, actually, for a natural phenomenon. and each side is being investigated as if the only things that were important were the velocity, the depth, the modulus. But there's also structural details here and there that change the picture a little bit. So actually, I think that is quite good. Now, that is with respect to VS30. Supposing we do what was suggested in the code and we use the velocity of the soil itself, the layer itself. Well, this is what you get. Now, you can't do much with that. You could force fit something there, but I don't think I'd want to try it. So it seems to me that using the velocity of the layer itself is not a good idea. Now, what about using the maximum amplification instead of the mean amplification? Most of our ground motion stuff, we're dealing with the mean, but in the maximum, there is a correlation. A weak one has only got about a 4.4, roughly. R squared is about 0.4. If you had to work with it, I suppose you could. But the mean is so much better. Now, how does our data compare with the data that underlies all the work in codes at the present time? This is work that was done for FEMA. It's in the American codes, and it is in our codes too, where we get our famous amplification factors. Now, they examine their data in different period ranges. This is the mid-period range, 0.4 to 2 seconds. And you can see that the data, all the data they're using, is within plus or minus 2 standard deviations. Now, that made us feel like we're not doing too badly because our data, for the limited 14 cases we've considered, are within 1 standard deviation. Now, when we do the other motions, that may not hold. I don't know, but I do want to do the other motions before I sign off on this kind of work. Now, something else happened that's very interesting. I showed this again just to show you what our correlation was like, plus or minus 1 standard deviation. Now, when FIBA, Borchardt, and the USGS were doing this work for the code way back in the 90s, they found something very interesting. They divided the amplifications up into different periods. You had short period, intermediate period, mid-period. That's the one we just looked at now. And the long, they do overlap. You see, the intermediate overlaps this one, part of it. But when they did that, what did they find? They found that you could, in fact, represent the results by just 2 curves. One for the short period, and if you're not fussy, one for the long period. And that's why we have 2 sets of amplification factors in the code. One for short period motions, one for velocity dependent or the longer period motions. Now, what did we find? Something very startling, actually. We found also 1 curve for short period, and you could say you could manage with 1 curve for long period if you were pushed. But it's reversed. It's reversed. Their short period is the low amplification. The longer periods are high amplification. It's the other way around for us. The reason for that is that their data is based on deep deposits. They always had 30 meters of soil with some to spare. Ours is shallow. And that accentuates because the period is linearly dependent on the thickness. So if you have a very thin thickness, your period is getting shorter and shorter. But we found that in the beginning, we found that quite startling, actually. Now, the big question is, nobody likes VS30. You go to a meeting of seismologists or people dealing with seismic hazard, they're all knocking VS30. But nobody has come up with something to replace it. They say, why should it work? Now, if you remember on my second slide, the period of the layer is 4H over Vs. Now, when you say Vs30 is the dominant factor, you're essentially saying H is a constant at 30 meters. And all that varies is V, is the velocity of the shear wave. Excuse me. Now, why did they pick 30 meters? Was there some scientific reason? No. It's the bottom, the depth of borehole you can advance in one day. Excuse me, I have a bit of a cold. But all their data borings for their instrumental sites are 30 meters. That's why they picked it. Well, we can understand why they picked it, but is it good? Well, we correlated the fundamental frequency of the site against VS30, not against H or VS, VH30. And we got a correlation 95% on the period. So this says whatever else VS30 is doing, it does seem to be related, or at least strongly correlated, with the site period. And the site period does influence the response. Now this result is not ours alone. Our colleague who did this using the total column instead of the top part, they found, Gofani et al., which was about 1 year ago, 2012, they found a strong correlation just like this. It's not quite as good as this one. I attribute that to the fact that they had a lot more sites in there than we have. So we may have been lucky with a good correlation. But we're going to look into that. But that was really surprising when we saw that. Couldn't believe it. Now, FEMA did divide things up into different categories and looked at the response, and we can do the same thing. So here is our three regions around 800, 400, and 300. So you might visualize those being as 250 to 350, 350 to 450, and 750 to 850. You can see now that for the high velocity, oh, damn it, I'm sorry. For the high velocity, the period is very short, 0.1 of a second. When you go to the 30 to the 400 meters, it's 0.15. Now, when you really soften it down to 300, then you're over at about 0.45. So the period is strongly dependent on the shear wave velocity, which is what we saw within the correlation with VS30. Now, we're certainly not going to make any recommendations for the code until we see the rest of the data to make sure it continues to support what's here. I'd say it's likely that it will, but will the correlations be as good? I don't know. We'll find out. But I think it's clear to me, at any rate, that we cannot decide on the amplification effects of the surface layer by simply looking at the velocity of the surface layer. It just doesn't seem to work. And therefore, I think we should go back to what we were doing before and make a VS30 out of it by picking up some of the harder stuff that's underneath, but making sure that the new correlation doesn't push us into the high, stiff areas like A and B, never going beyond the C. Well, that's my story. My colleague, Francisco Ruz, was here for a year. He did his master's degree here. His family have a fairly medium-sized engineering firm in Chile. He's back there now working there, and he's devoting some time to running off the rest of our ground motions. We hope that before the end of the year, we'll close the book on this, and hopefully we won't have to change our preliminary ideas very radically. Thank you very much.
Okay. This is forward. Okay, well, I'll introduce myself. I'm Professor Schwinar from McGill University. And my talk is to present some of the microzonation maps we did for Montreal and the suburbs. So my presentation, a brief outline, first looks a little bit at the historical, the earthquake history in the greater Montreal area. So we're not a seismically active area like Vancouver, but we're still a moderately active area where seismic hazards are important. Oh, this doesn't work? Oh, sorry. Oh, didn't realize. I'll talk a lot about site amplification due to surface geology, how we did site characterization in Montreal, talk a little bit about site-specific analysis we did, and finally talk about some of the applications dealing with risk analysis. Just to give a little bit of perspective where we're located at the other side of the country, for those who are not familiar with Quebec. So Montreal is located in this area here. So visually you can see that it's an area that's much less active than it is on the West Coast, but it is there's a significant amount of activity, be it somewhat of a lesser magnitude. This is a compilation of data dating from years 1627 to 2009. So why talk about seismic risks in Montreal if we have moderate seismicity? Is that if we combine the population that is exposed to potential earthquakes, and we look also at the total built environment and the age of the structures that we have, combining the hazards with the potential consequences, we rate, according to the Geological Survey of Canada, second in Canada in terms of major areas with respect to seismic hazards. Now, if we look a little more closely to the seismic setting around Montreal, we're in an intraplate region, so we don't have as well-defined sources of earthquake as you have here on the West Coast. And there's two major systems that seem to contribute mostly to the earthquake activity in the Montreal area. One is part of a, One is part of a failed risk system that follows the St. Lawrence Valley and Ottawa River Valley. And the second system was formed by a hotspot that had been moving below the Earth's crust, which created a zone of weakness in the rock, which is the second region where we have major earthquakes. The largest earthquake recorded, not recorded, but reported in the Montreal area is assumed to have occurred in 1732, and the magnitude of the event that has been inferred from reports is that it was of magnitude of 5.8. We do have quite a bit of activity, and this just shows some of the recent events that we've had. So they're pretty small, the ones that we've experienced lately, but we see that over the last 10 years we had at least 5 events. And if we look at the way the events have been reported, we see that it is shaking the grounds in a significant way, enough to generate a lot of these felt reports that are then compiled by the Geological Survey of Canada. So in terms of the side effects, the ones that I'm looking at here are going to be restricted to only the side effects associated with soil amplifications, but there are other types of soil movements that are of interest when we're talking about seismic hazards. There's, of course, liquefaction. You can also have rock falls. You can have amplifications due to topography, slope failures, or surface ruptures. So the ones that were of interest for this presentation are the ones limited to soil amplification. This illustrates the effect of soil amplification on earthquake signals. So this is actual data that was recorded in a valley in the Alps. And this shows the rock motions that were recorded on rock, and then compares the rock motion, the ground motions that were recorded at various locations across the valley. So what this exemplifies is, first of all, the amplification of the signal itself compared to the ones that we have at the rock, but also the elongation of the signal. So there is both an amplification, but also an elongation of the duration of the ground shaking due to the presence of the soft soil. This shows a little bit what we can record with the smaller events that we have in Montreal. So on this map, what you have is the location of 4 accelerometers that were installed in buildings in Montreal. And these are accelerometers that were provided by the Geological Survey of Canada. And on this map, what we're showing in red are the regions where the soft sediments are the thickest. And this kind of even shows for a small event that where we have the thicker soil deposits, we do have this effect of amplification compared to sites where we're close to the rock surface. By the way, all the sites in Montreal would qualify to the definition of Professor Finn of having thin soil deposits, since the maximum depth for our soft soil deposit is probably at the tip of the island here, and that's about 30 meters. So for the microzonation of Montreal, we had several sources of data. The first one that we used was a database on boreholes, and the database that we had contains over 20,000 boreholes. So all the little red dots that we see here correspond to the location of one of these boreholes. And as you see, it's not very uniformly distributed, and that's normal because it's kind of correlated to the construction of aqueducts and highways. But from this data set, what we can do is to infer a map of depth to bedrock across the region. And what we find is that the depth to bedrock is the highest here at the tip of the island, along the eastern shore of the island, and in some areas, like in this area here, close to downtown. The other source of information we had to start with was a map of the surface geology. And this was of interest to identify zones where potentially we would have soft soil deposits. So the ones that are to look for are the ones where we have sand and clay, corresponding to the kind of yellowish regions and the blue regions on this map. So if I go back to this one, the interesting thing about this is that the blue region of this map is a region corresponding to the Port of Montreal. It covers part of the downtown of Montreal, where we have a high concentration of buildings, and the plateau, the Montreal West area, also where we have a high density of population. Now this shows an example of amplification that occurred during the Saguenay event. So that was in 1998, so about 25 years ago. It was a magnitude 5.9 event that occurred with the epicenter about 300 kilometers from Montreal. So one of the characteristics of the earthquakes in the eastern part of Canada is that they're felt over very large regions. The attenuation is very slow. And this kind of exemplifies the type of amplifications we can have even at far distances. So even at 200 kilometers from the epicenters, we had some damage to the masonry of the Montreal East City Hall due to the soil motions. And it is interesting to note that this location is a site where we have 17 meters of soft clay deposits. To be totally honest, the building was not in the best shape. It was an older building, but even so, it's interesting to know that we can have this type of damage even 300 kilometers away from the epicenter. So the current building code has a table that helps you classify your soils as being of different types, as Professor Finn mentioned. Here I highlighted the part that deals with the shear wave velocity because this was the main part of our work to come up with a good characterization of shear wave velocity profiles for different types of soil deposits in Montreal. So to do this, there are several field procedures that can be used. Actually, if you're interested, there's a very good document that was produced by the Geological Survey of Canada, and I gave you the reference here, that basically summarizes the practices for soil characterization in Canada. The ones we use in Montreal is a mixture of various methods. The first one is based on borehole surveys. So the borehole surveys are pretty good and accurate. The only problem is that in order to make the measurements, you need to have a borehole available, and it has to be cased, and it has to have the right diameter in order to put in your instrument and be able to make the measurements. So we did a few of those, but they require extra cost, and you have to do extra planning, so it's a little bit difficult to do this in a systematic way. The other way we did the measurements is through seismic reflection and refraction. So this is a very good way also of getting some data. The only disadvantage here is that you have to have a large area that is available for making the measurements. So typically you can only do these in parks where you have enough length to deploy your instruments. The other type of survey we did with the Geological Survey of Canada is to use what they call the streamer with their mini-vibe. And this is basically a seismic reflection refraction, but this you can do on roads. And using this procedure, we did over 8 kilometers of surveys across Montreal. And from this information, you can get profiles, velocity profiles for shear wave velocity. The last method we did in terms of field surveys is to use measurements of ambient noise. And this is what we call the H over V method of characterization. And the information that you get from this type of survey is the fundamental period of the soil deposit. And you can also use, in some cases, forward modeling to get some estimate of the shear velocity profile. So this shows all the measurements that we had collected over a period of perhaps 10 years. So we covered most of the island of Montreal. We covered also some of the suburbs south of Montreal and north of Montreal. And we also provided different types of maps. So the first map here is one where we give the fundamental frequency of the deposits as a function of location. And as Professor Finn showed, this is highly correlated also to the thickness of the soft soil deposits. So if I go to the next slide, this is our map of thickness of soft soil deposits. And if we compare the two maps, we see that there's a very good correlation between the areas that are deeper and the inferred values for the frequency, the fundamental frequency of the deposits. The other thing we did is we created a multi-layer model. So we had enough data at about 2,000 boreholes in order to infer the variation of thickness of different soil layers. So we look at thickness of sand layers, clay layers, and adapted bedrock, and created a 3D model across the island. Next, we compiled our data. So this shows some of the data we got for depth velocity curves, for shear wave velocities, for sand, and for clay. And we did also some correlations between fundamental frequency. And here, I don't show it with respect to amplification factor, but we did try to correlate it to VS30 and found some correlation between the two. And this shows the compilation of the map. So the compilation of the map is one where we use the data from seismic surveys. We use the data also from the boreholes and the data from our 3D surface geology model. And this shows that we have some zones where we have some D. So the zones where we have a lot of clay, thick clay and thick sand layers are shown here as D. They're mainly located at the tip of the island and along this part where we have the port facilities for Montreal. Then we have some zones near the downtown area and some residential areas. And the rest of the island has, much shallower sediments and a lot of till close to the surface. So we classified it, a big part of the island, as B. So this shows an application of this map. So using the map, what we can do analysis of scenario earthquakes. So this was for a scenario of an earthquake with an epicenter somewhere in the vicinity of this part of the island, about 30 kilometers from the island. And these shows the contour lines of spectral acceleration at the period of 0.3 seconds. And the effect of the soil amplification is shown here by modifying the contour lines of the spectral accelerations. And this type of information then is combined with data sets on buildings. So we have information on type of buildings, year of construction, so we can correlate this to fragility curves and come up with estimates of damage for the scenario. So to conclude, Montreal, the greater Montreal area is an area where we have moderate seismic activity, but where large earthquake can have a significant impact because of the density of population and the built environment. We did a soil mapping following the NBCC 2010 and is available now, but it needs to be completed, improved, and expanded to include additional areas around Montreal. The map shows zones with expected site amplifications, where the site amplifications now are based on the current code, but the data we have actually could be used with any type of modifications that could come with the future generations of the code, since all the data we have is based on the shear wave velocity profiles. This can be combined with evaluation of vulnerability of existing buildings to evaluate risks for various scenarios. And another application of the microzonation map is that we can couple this with shake maps to get better estimates of ground motions following an earthquake by using the shake maps that have been produced that are being basically administered by Gal Atkinson and her group. So that's it. I don't know if you have any questions.
We have a few minutes. He finished early, so if you have any questions. Any questions? Okay, thank you very much. Frequency, you probably. Our next is Dr. Freddie Una. And Freddie came here and did his PhD here, and went back to Chile for a while. And he returned, was postdoctoral fellow. He's worked downtown, and he's back now in the role of consultant to the SNOOS project, and to which he has contributed some very original work. So Freddie, we will talk about intraplate earthquakes, huh?
Yes.
Okay, go ahead.
Keeping the same.
Let me start you right here. Come on. Put it on 0 for him. Okay, off you go, Freddie.
Thank you. Thank you, Dr. Fink. Okay, good afternoon. What I'll be presenting today is research work that I did when I was in Chile like 2 years ago, and then some of the students continue that research, and there were some other professors there and researchers that continue that work. And what I'm trying to do now is to explore whatever we find from this research for the schools project in BC. That will start next year. So I'll explain that through the presentation. So I'm not going to explain what is a subduction zone, but what I'm showing with this cartoon over here is all these dots here that we have are the earthquakes that we observe every day around the world. And if you take a closer look to every subduction zone in the world, you will see many dots with a depth of more than 50 or 60 kilometers. What is that doing to our structure? That was the main motivation that we had. We know that we have pretty good data right now, but there's a lack of correlation between what is really happening on the ground and what is actually happening to the structures that are right above those earthquakes happening. So here is just a screenshot I got like a week ago. You can see all the subduction zones in the world. We were more interested here in this part of the world. And if you take a closer look to each of those zones where you have those many dots, you start seeing a lot of them with the green color, which are deep earthquakes. What it's telling you is like the rate of occurrence of these earthquakes is pretty much the same as the one for subduction or even crustal in the same zone. So the same happening here. If you go to Japan, well, you don't see that many here because you have the latest activity from the Tohoku earthquake. You have a lot of aftershocks, but you still see some green dots that are pretty much in the same rate of occurrence of the other type of earthquakes. So some of the few cases where you can actually see damage for these type of earthquakes, I will show here in probably 4 cases. This was when in Japan, in Geijo, southern Japan in 2001, magnitude 6.7, and this was an earthquake like 50 kilometers down, and then 3,700 buildings were damaged, and unfortunately 2 people died after this earthquake. But what I want to show here is the type of building, the type of structure that is always involved with lots of damage for this type of earthquake, which is heavy and very stiff structure. In the same year, this was pretty close to Vancouver. It was in Seattle, Nisqually area, 2001. It was about 52 kilometers. It was reported like 1 billion losses, most of them non-structural related damage, and it was one death and more than 400 people injured. Most of them due to the falling of non-structural components from very rigid. There was a lack of ductility in most of the structural systems. You start seeing the same type of failure for this type of earthquakes. Then again, El Salvador, this was in 2001 again. It was a magnitude 7.7. This one occurred in January. Then they had another one in February, almost the same magnitude, but this was a deep earthquake. It was about 60 kilometers. That was the dip. 1.2 billion losses again, and 60,000 people were homeless, most of them related to landslides in the country. And in Chile, we have a couple of examples too. We have a lot of these earthquakes happening in Chile, but most of them occur where there's no population living there right above where these earthquakes occur. But we have like 2 cases. This was in Punitaqui. It's very close to Santiago. This was about 100 kilometers depth, and we had 8 people dying and more than 60,000 people homeless. And again, the type of structure, rigid and heavy, most of the time in poor sectors of the country. So we're dividing this research study into 2 parts. The first one is the one that people still are working there in Chile. What I'm showing right here is going to be just a preliminary risk estimate that we did for the city of Santiago. The government there was more interested in comparing what this type of earthquake will do to the structures compared to subduction earthquakes, which are the major earthquakes that we have in Chile. And the second part will be to do pretty much the same, but we have a different methodology for the schools project here, and we apply the same using a different set of ground motions for deep earthquakes than the ones that we have, and we will start observing differences, but in terms of the overall risk for the schools. So in the case of Santiago, a little bit of geography. This is the trench. Most of the subduction earthquakes happen between this red line and somewhere between Santiago and Valparaiso. The one that you heard in 2010, magnitude 8.8, was a little bit south of this region, but the rupture area was pretty much here, ended up here. And from here to the mountains, you have a combination of earthquakes types. You have some of them crustal, subcrustal, like deep earthquakes, and subduction earthquakes affecting the hazard of that part of the country. If you want to see a profile of this, then we have the coast. Here would be Santiago, the mountain, and here all the earthquakes that we selected, that we could select from public database. So these are all the earthquakes that we play with, just to see how they affect the structures that are right above here in Santiago. So here's more information about the earthquake we selected. We have 5 subduction earthquakes and 9 deep earthquakes with magnitudes that are considered to cause some damage to the structural systems. So if we look at the spectra, the response spectra, the response acceleration spectra for Santiago, you see here the black line is the latest design spectrum that we use for buildings, and these red colors are for deep earthquakes and the blue colors are for subduction earthquakes. So we start seeing like big differences in both type of earthquakes. If we look at the maximum values, you see that the contribution to hazard for deep earthquake for a very short period, it's significant compared to subduction earthquakes. For the rest of the structures that are with a longer period, then the subduction dominates the hazard for periods up to 4 seconds we have here. If we remove those maximum values, because we're more interested in the, we call it 84th percentile, which is the mean plus 1 standard deviation, we see that the black line, well, there's no clear pattern of what is really following, but what I can tell is like it's always updated after a big subduction. The code doesn't take into account the effect of other earthquake types. So that was our main concern, like how to deal with these earthquakes that are not part of the code requirements right now. So if we compare just the ground motions, the response at the surface, we have that subduction earthquakes are dominating for most of the periods ranges, and if we look at deep earthquakes, they are dominating for a particular region for very rigid structures. However, the government wanted to see not just the ground motions, they want to see what is the effect of this, for the entire city. So that was a big challenge. They ask you to do that, but there's no enough funding to do that. So we came up with a very fast solution on top. We're using undergraduate students, like they don't have enough background to run nonlinear dynamic analysis, all that complicated stuff. So we came up with a procedure based on nonlinear spectrum analysis. We just count the number of events that are above inelastic spectrum, and then we decided, well, if it's above that nonlinear spectrum, well, you'll probably have some damage, or you'll probably, what we call, you're going to be above the code, and you decide if the structure is okay or not. So we have about 34 municipalities in the Greater Santiago. It's a 5.4 million people and around 1.5 million houses that we had in the Greater Santiago in urban areas. Most of them are houses, 1 to 2 story houses. Most of them are confined masonry structures, and there is like 20% of them buildings, but these are heavy buildings. These are shear walls buildings. This is shear wall paradise in Santiago. You can see here the type of structures. This is a typical house in Santiago, a 2-story building, confined masonry. The brick is part of the frame. Then there is this type that is also common. You have confined masonry here, and you have a wood structure on top. And the shear walls in buildings. That's very common. If you go to Santiago, you see this type of structure everywhere. I'm showing these 3 because they behave pretty well with big earthquakes, and it's been showing that like for a long time. So here's the distribution of all the municipalities in Santiago, and here you see how the confined masonry houses are distributed. It's pretty much all over the place. Buildings are in the nice parts of the city. You probably, when you go to Santiago, you go to this part. This is the airport, but then you travel right away to this part, and this is the nice part. The rest is all houses and suburban areas. Here you see with houses, most of them are with not the best quality of construction systems here. Okay, so once we divide the city into these different districts, and then we identify the percentage of housing in each of these municipalities, we group them in terms of structural prototypes or structural systems. These are our main systems here. This one is wrong. This one should be wood. And then we have here the main description of the system, the number of stories, the percentage of them in Santiago. So you can see right away, like 50% of them are housing confined masonry. That's the typical system in maybe in the whole Latin America or South America. You can tell, Jose. We estimated the period. This is the number of floors divided by 10. It's pretty close because they're very rigid, the structures in Chile. We estimate the ductility and the R factor, so we can calculate a nonlinear response of a single degree of freedom system and then do the counting. So this is what we did. We ran that for all these 300 or 350 ground motions that we have. We separated into deep earthquakes and into subduction earthquakes. We plot the code. This is the design code now that includes the R factor. You can start. You can see right now like how many of them are above for this short period, and this is where we actually see a lot of damage. But this is for the type of structure where we actually see damage for deep earthquakes. We don't see damage for buildings, for 4-story above, but we do see that for subduction earthquakes all the time. So we ran that for better. Oh yeah, I just put the title. I hope that the whole picture we can understand.
Before picture, the blue is
the blue ones is subduction earthquakes, and the red one is deep earthquakes. Thank you, Jose, because this is in Spanish. So, and again, here we have a mix of colors. We have the magenta or whatever purple is subduction earthquakes, and the green ones are deep earthquakes. This is for a ductility of 6. We start seeing, but the period of the structure is somewhere here. So most of the cases where above the code are just for subduction earthquakes. So if we go with the counting process and then we include the percentage of the houses in the city, we end up with a risk estimate, and risk for us is the probability of code values being exceeded. The government agree with that, and then we decided to go with this definition. And then we add them up, and then we have a risk value at the end. They were pretty much the same. But if we deaggregate that risk for all these different type of structural system, we see that the main difference is here. And that's when we start having some issues here in Santiago, because most of the structures are in this group. So here the main comments. Obviously, after this study, well, we have to do some more. There are other universities involved as well. We need to include that with a different value for the plateau in the short periods. And there is also something interesting that we found, that the deep earthquake, the contribution to risk is pretty much the same for the entire range of periods in the spectrum. So they would contribute to the hazard as well as subduction earthquakes. So that's what we did in Santiago, and this is what we will do here. First of all, we had to define those values in Chile, but in the next part, the SRG, the Seismic Retrofit Guidelines, this is for the schools project here in British Columbia. We will run a couple of examples for a new set of ground motions for deep earthquakes for the cities of Vancouver, Victoria, and for the interior BC. And we will use the same methodology that we have for the schools project for the city of Santiago, and then we correlate with whatever we've done before. And the idea of this is to define a new set of ground motions that we can use at the end to calculate the risk, and the Ministry of Education can have a better handle of the risk values to prioritize the fundings for retrofit of the schools. So here's the region here, southern BC. We have Vancouver over here, Victoria. Here would be the trench where the subduction earthquakes will occur from here up to somewhere here. And then all of this zone here will be, the hazard will be dominated by deep earthquakes. So if you go to the Geological Survey of Canada, you would see marked with these two regions where we are expecting some type of subcrustal events occurring and dominating the hazard. If we see that in terms of the spectral values for the code, then here I still have the same plot as before. I just added the subcrustal events, or the deep events, for Vancouver. And here you can see the shape. And here you see this would be the mean plus one standard deviation of the previous study. Of course, we have to select different ground motions. Probably the hazards are different between Santiago and Vancouver, but I'm not expecting to be that much different. Some interesting thing, if we compare the maximum, of course, there's nothing there that we are picking from our curve. But what I'm showing here is not the actual value that we have to match. It's because we have an issue here with the scaling procedure. If we go to periods where we think most of the structure will behave, like we pick for the schools project a range of periods between 1 second and 2 seconds. So if we look at the values here, we will probably be scaling every ground motions that we have to match this green line. So we will end up with factors of 3, 4, 5, just to match this curve. But when we amplify this for the same factor, we will be amplifying these big values sometimes because this is the shape of this type of earthquakes, and we will end up with values that are sometimes 6, 7, 8, 10, that we've never seen from all the ground motions that we have so far. So this is one of the main issues that we have in the schools project. 2 minutes. I'm done. So here would be this is the recommendation right now. We have 3 sets of ground motions. We have for shallow crustal, we have for subcrustal, deep earthquakes, and then for subduction. We're interested right now in this one. The way we are scaling the ground motions are between 1 and 2 seconds. and I think that's wrong. We should be scaling this in the period range where we actually interested to avoid damage for this type of earthquake, which is for short periods. So my recommendation, or our recommendation from previous studies, to scale something closer to PGA, or the maximum expected acceleration of the spectrum. And then, well, this is for subduction earthquake. This was part of another study, but it's also a part of the new research that we'll be following here in BC for the schools. I think that's it I remove a lot of slides just to keep that in time. Okay, thank you.
I think we have time for one question.
No question. Should I keep that open? No, because I may have some random.
Set that to 0 for me again. Yes. Our next speaker is Manuel Archila. He's a PhD candidate. And he's concerned about the effect of directivity on tall buildings. His work actually is very, very interesting. Manuel. Look over once in a while. Yeah.
So, is that like this? Okay, good. Okay, so as we just saw Freddie's presentation, we have the risk in Vancouver, in British Columbia, of deep earthquakes, but at the same time, we also have the risk of having a shallow earthquake near a urban center, and that in the past has resulted in what is called forward directivity effects in some places, and also directionality of the ground motions has been important. After the damaging earthquakes of Northridge in 1994 and Cove in 1995, a strong polarity in the ground motions was observed. The studies attributed the damage to tall buildings to the presence of long period pulses from rupture directivity. And after these earthquakes, the potential damage that these ground motions pose for the built environment triggered the adoption of some amplification factors in the design spectrum of the UBC code in 97. That's the code that they had in the US back then. So after this updated code, there were many studies that were done to address the effect of directivity on the response of buildings. There was one very important study by Paul Somerville and some of his colleagues in 97 that concluded that forward directivity caused ground motions to have a very long period pulse in the strike normal component, usually at periods longer than 0.6 seconds. All these studies overall concluded that forward directivity was very important for structures having long periods and in the near fault area. Now, recently, there are other studies that are going on forward directivity and are trying to better understand this effect. But before I continue, I just want to give you a brief explanation of what rupture directivity is. The way it's been defined by Somerville is that when your site is located near a fault, you need to meet two conditions to have the effect of forward directivity. The first one is that the rupture front needs to propagate toward the sides. That's as it's shown. Let's see, I don't know. There, this is the epicenter, and the rupture on the fault is propagating to this location. That's the first condition that was met in this recording from Lander's earthquake. And the other condition is that the direction of the slip has to be aligned with the sites, and it's also met on this site. That results in a ground motion that has a very long period pulse of big amplitude, of large amplitude in this area. On the other side, down here, away from the front of the wave propagation, you have a very long period, or a very long record that has many cycles, but you don't have big amplitudes. So that's one of the differences between these two records. This is a short duration record of very long period pulse, where here you have many cycles and long duration of the record. So this has become a concern for tall buildings because they are long period structures, and bridges as well. All this was defined in the context of forward directivity. When we come to Vancouver and we see how the magnitude distance deaggregation is for the seismic hazard from shallow earthquakes, we see that the mean magnitude is around 7 and the distance is 19 kilometers. That means that definitely we have some significant contribution from near fault earthquakes into our seismicity. And we need to better understand what is the effect of these near fault earthquakes on structures to see if we need to make some changes to the way we design our structures. To do this, we are doing a study with Professor Ventura and Professor Finn, and we are studying the behavior of tall buildings using ground motions that are representative of the hazard in Vancouver. So this is one example of a ground motion pair that we have selected. This is a record that was obtained during the Imperial Valley earthquake in 1979. It was a magnitude 6.5, and it was recorded at a distance of 10 kilometers. We have on the black line here, the uniform hazard spectrum for Vancouver, 2% in 50 years. The red line represents the spectrum that is obtained from the fault normal component. The blue line represents the spectrum that is obtained from the fault parallel component. And the dashed line is the geometric mean of the two components. The study that Paul Somerville did in 1997 concluded that the fault normal component was the one that will be associated with a strong shaking of or long period pulses in the long period range. But in this case, we can see that below 3.5 seconds, the fault normal component is not dominant. Instead, it's the fault parallel component that is giving the largest demands on this case. So this has required from us to investigate what's going on with these ground motions when we look at them at different orientations. It looks like the fault normal component is not always relevant as we thought, and in this case, it's the fault parallel component that we need to be concerned about. So here I have an animation that shows how the response spectrum is affected when we resolve the two. Sorry, go ahead. When we resolve the two horizontal components at different orientations, we are rotating the pair of ground motions, and we see how the amplitudes change. And there is a big variation that is happening in the long period range. Can you just click? we see that in this case, there is one component that dominates completely the spectrum, but it's dependent on the orientation of the ground motions. In some cases, we will see that there is a change. The dominant component is this, and then after 2.5 seconds, it comes down. So definitely, we cannot say that there is a certain component that will dominate the spectrum over the entire period range. We need to better understand what's going on with the ground motions and the physical process behind these earthquakes. To complement our study, besides studying the effect on single degree of freedom systems, we have worked some case studies. This is one of the buildings that we are analyzing, and this is a 30-story building in downtown Vancouver. It is a reinforced concrete building that has core walls that are coupled through coupling beams. The building was instrumented by Professor Ventura and his students in 1996, and they determined the dynamic properties of the building. It has a fundamental period of 1.8 seconds in the north-south direction. We have developed a nonlinear model based on the characteristics of this building, and we have been able to calibrate our model to these dynamic properties. We are using this ground motion and other ground motions to study what happens to a tall building in Vancouver when these ground motions have forward directivity effects and also directionality effects. The first exercise that we did was a linear analysis. So we rotated the ground motions at a step angle of 10 degrees, and we determined what is the displacement response of the building. And it's shown for all the cases with a gray line. And for the fault normal components, we show the response in a red line. And when the fault parallel component is being applied, we show it with the blue line. Again, Paul Somerville generalized that this component was going to be dominant. For this particular case, under linear response, we see that there is almost the minimum response that we have. On this side of the plot, we're showing the angle that will give us the largest response over all the possible angles of incidence. And for linear response, it's 0 degrees. That is associated with the fault parallel component in our case. Here, the amplification makes the ratio between the largest response, that is called the critical response, and the response that we have under the fault normal component. And we are seeing an amplification of the order of 3. That is something that we did not expect from a near fault earthquake, but our study and recent studies that are being conducted in the United States as part of the NGA West 2 project has confirmed the same observation for single degree of freedom systems. That not always the fault normal component is the dominant in the near fault area. The second set of simulations was to study the nonlinear response of the building. And when we compare these two responses, we see a drastic change. During the linear response, the fault parallel component is giving us the largest response. When we are doing the nonlinear response, we see that the fault parallel component is no longer dominant. And now the fault normal component is becoming a little bit more important. Now the angle that will give us the largest response is 40 degrees, is no longer 0 degrees, and the amplification that we have at the critical angle of incidence with respect to the fault normal component has reduced to a factor of 2. And we can better illustrate it here. the thick line is the response that we obtain from a nonlinear analysis. On the horizontal axis, we have the angle of incidence of the ground motion, and here we have the roof displacement. We can see that, first of all, the response is quite different. There is a big amplification on the responses. And what is called the critical angle of incidence for the linear response is not near close to the response that we have when the response is nonlinear. The critical angle changes, as we saw in the previous plots. So what is going on with the response of the building that is causing these differences between the linear and nonlinear response? And that's something that we are trying to understand. Some of the explanation that we expect to present will be based on these. This time series shows the response of the building, the roof displacement of the building under nonlinear response at the critical angle of incidence. This second plot shows the instantaneous period of the building normalized by the elastic period, fundamental period of the building. And we see that it changes between 1 and 3 over the entire response. And down here, we have the input motion. This is the ground velocity time series. This pulse has a period of 3.6 seconds. And we can see that we have a single pulse that is associated with this response of the building, that we don't have many cycles of displacement. We just have a big response, and then the response decays. In this case, the ratio of the period of the pulse to the elastic period of the building is 2. And this is something that we are trying to correlate with the degradation of the stiffness of the building. Professor Oliver is also doing some work on that, and they are coming with factors to reduce the stiffness of the building, trying to obtain a better estimate of the displacement demands that the building will experience when the response is nonlinear, and this is correlated with that effect. The dominant period of the ground motion has an effect on the response when it, in this case, it has a ratio of 2 with the fundamental period of the structure. In many cases, we think that the ratio of between the pulse and the period of the pulse and the period of the building has to be 1 in order to have the largest response, but we are finding that usually we have a very large response when the period of the pulse is larger than the period of the structure. Just some remarks. So far, we have found that the fault normal component is not always dominant, as we originally thought from previous studies. The critical angle of incidence that we obtain from a linear analysis is not always the same that we obtain or we expect from a nonlinear analysis. And the displacements that we predict from linear analysis can significantly underestimate the displacements that we obtain during nonlinear analysis when the ground motion has long period pulses. That's all. Thank you.
Any questions from Manuel? We have 2 minutes. No? Thank you very much, Manuel. That's very well. Our next speaker is Ms. Sophia Zhao, who will talk about the effect of vertical ground motion.
everyone. Good afternoon. My name is Sophia, and I just finished my 4th year study here in UBC as an undergraduate student. It is truly my honor today to stand here and talk about the research I've done with Dr. Tony Yang in the past 2 years. The topic of today's talk is vertical ground motion effects on high-rise buildings. As we all know, horizontal ground motions have already been extensively studied and included in design building codes, while the vertical ground motions didn't attract a lot of attention yet because of the 2 major reasons. The first one is lower energy content compared to horizontal components. And the second one is a lot of people argue because a large safety factor against the gravity loads has already been used in the design, so we don't need to worry about the vertical ground motion anymore. Those 2 thoughts have been taken as granted in the past few decades until the occurrence of the Northridge earthquake in California in 1994. This Northridge earthquake was a milestone in the study of vertical ground motions because it was the first time that researchers got a chance to set up equipment to capture the vertical ground motions and study its potential effects on modern buildings. The peak vertical ground motion reached as high as 1.18 G in Northridge earthquake, and let me give you a general sense of how big that is. People can start to feel the ground shaking when the ground motion is around 0.002 G, and the people start to lose their balance when the ground motion is around 0.02 G. And only well-designed and constructed structures can survive a ground motion of 0.5 G. And here it is 1.18 G, so you can tell how strong that earthquake was. And the peak vertical to horizontal ratio reached as high as 1.79, and this ratio is always treated as 2/3 in most of the design criteria. A lot of structure failed in that earthquake. It might be due to different reasons, such as high mode response, abrupt changes of stiffness and strength in elevation, or even the lack of capacity on high stories. However, there are a lot of site evidence show the brittle failure by direct compression of members and the reduction of shear and flexure strength and ductility due to the oscillation of axial force in columns. Here, I'd like to show you some site evidence of structural failure caused directly by vertical ground motions. This picture shows the symmetrical compressive column failure in a residential building. This second one, this building completely lost its 2nd floor due to the shear failure in the column and the beam column connection. This shear capacity reduction might be due to the reduction in the axial force in the column. This third one is a puncture shear failure of upper floor in the mall. It's a puncture shear failure mode because you can still see those columns intact still after the earthquake. And here I'd like to show you a simulation done by Dr. Gregory Sulazinski. It might not be the best animation, however, it gives you a general sense of how the stress accumulates and how the building progressively fails under the vertical impulse. You can see the vertical ground motion triggers the oscillation of the slab. Then the column slab joints start to fail. Then finally, the slab starts to collapse. After the entire failure of the structure, the columns are still intact. Okay, so after we've seen all those evidence showing the importance of vertical ground motions, we decided to look into the vertical ground motion characteristics and its potential effects on high-rise buildings. Horizontal ground motion is more associated with P wave, and the vertical ground motion is more associated with S wave. P wave, as we can see here, has a longer period with higher overall energy content, while the S wave has shorter period with a lower overall energy content. Although the vertical S wave has lower overall energy content, it occurs in a shorter period of time, so the energy might concentrate more in a shorter period of time. Plus, for most of the buildings, the vertical stiffness of the building is stiffer in the vertical direction. So the S wave is more likely to resonate with the vertical period of the building. Sorry. Yeah. Okay, so after reviewing thousands of ground motions in the past, Nazi and Bozognia conclude that vertical ground motion is a strong function of oscillator period, source to site distance, and the local soil condition, while it's a weaker function of earthquake magnitude and type of faulting. However, not all those effects have been considered in the recent design code. For example, in UBC 97, section 1631.2, it says the vertical component of ground motion may be defined by scaling corresponding horizontal acceleration by a factor of 2/3, and alternative factors may be used when substantiated by site-specific data. However, this clause only includes the site-to-source distance factor, while it ignores other potential factors mentioned on the previous slides. And this is about the ground motion part. And in order to better understand the performance of high-rise buildings under vertical ground motion, I did an analytical assessment of a 42-story building located in Los Angeles, California. This building is represents typical core wall high-rise buildings located on the west coast of California in the United States. And it's a well-designed and engineered building following the 2006 International Building Code. This slide shows the isotropic view and plan view of this high-rise building. And complete nonlinear finite element model was built in Perform 3D. The core wall was modeled as nonlinear fiber section with both the in-plane and out-of-plane shear response modeled elastically. The nonlinear coupling wall have been modeled wherever there are openings in the core wall. Basement walls were modeled as elastic shear wall elements. And of course, the mass was distributed to each node using the tributary area method. The ground motion used in this study was selected based on the site-specific spectrum for this prototype building. And 5 hazard levels represent the return period of 4,975 years, 2,475 years, 475 years, 43 years, and 25 years, respectively. And they're denoted as OVE, MCE, DBE, SLE 43, and SLE 25. Those ground motions, 15 different sets of ground motions have been selected for each hazard level, and they're all scaled in a way that the geometric mean of the horizontal pair of the ground motion meets the target spectrum. The vertical ground motion was scaled using the same factor. So this picture shows the VH ratio and the ratio of the arrival time. You can see the average VH ratio is around 2/3. However, for some of the megaquakes, such as OVE, the ratio can be as high as 1.8. The ratio of the arrival time average is around 1, which means both the horizontal and the vertical ground motion arrive pretty much at the same time. And the two separate models were run with and without vertical ground motions, and a bunch of structural response were recorded and plotted here. As you can see here, the green line indicates the ratio of each set of ground motion and all the response under each set of ground motion. The red line is the average, and the green line, the blue line is the average plus 1 standard deviation. Not surprisingly, the interstory drift ratio and the horizontal floor acceleration didn't change quite a lot if we do include the vertical acceleration. The same thing happened to the shear force and moment in the core wall. They didn't change quite a lot either. However, as expected, the axial force in the core wall and the vertical floor acceleration do increase drastically after we include the vertical direction ground motion. For the axial force in the core wall, it increases as the floor level goes up, and it's more obvious for ground level with higher intensity, such as OVE. In order to better understand the effects of including the diaphragm system in this model, we further modified the original model to include the diaphragm system as well. And the ground motion with the highest intensity, which is OVE, was run in this case. Not surprisingly, the structural response, such as the interstory drift ratio, the horizontal floor acceleration, and the moment and the shear force in the core wall didn't change a lot. However, the axial force in the core wall increased again in this case, but the shape of the plot was not exactly the same as we previously saw, which needs to be further investigated in the future study. And to conclude and do some recommendations, after we've seen all the results, we can tell that the vertical ground motion does increase the axial force in structural components, and it may lead to other potential shear and moment capacity reduction and ductility reduction. So maybe more attention needs to be paid in the further, in future building design. And in terms of the 2/3 scaling factor used to scale the vertical ground motion, those people have come up with 2 simplified methods to more accurately scale the vertical spectrum. However, the accuracy of those 2 simplified methods needs to be further investigated. And that concludes my presentation.
Questions, anybody? Can we entice anybody to ask? There we go.
Sorry, very nice presentation, but I had trouble reading your slides. So I think just in simple terms, the axial load increased in the gravity columns by how much?
By about 1.5 centimeters.
In the gravity columns?
In all the columns.
In all the columns. 50% increase. Thank you.
Very, it's only on the base.
At the very bottom. So that last plot showed that increase in duration. Yeah. Well, that's a pretty significant increase, isn't it? Although we designed for gravity loads that are generally much higher than what we get in earthquakes. I worry more about things like transfers, right? I mean, big, heavy transfers that are already loaded with gravity loads, when you suddenly then have a vertical force. Whether that might be really a concern.
Since we now have many vertical cars with horizontal contours, why do we have to worry about scaling by some artificial means? You get the periods right, you get the everything, well, because it's what we've got.
And scale in proportion to the sheet.
The first instance that I recall of vertical ground motions being brought into space in 1966 in the Tashkent, where they had a building that the aircraft protected in the main city. And it wasn't a big one, it was more than 6. But there was a lot of cracking near the roof, especially, and also under the hard floors, which was attributed to the vertical propagation of vertical shear wave, vertical motion. And then in the reverse, you have the double motion. We're going for our coffee now, but I think it would be fair to say that there was a very interesting cross-section of papers with our students, both at Tongji and UBC, are engaged in very significant work, quite advanced work. I think we congratulate them on the terrific job they've both done. So thank you all very much.